Hello, my name is Yutao Liu. I'm a PhD student in the University of Chicago. My advisor is Peter May. In this video, I want to talk about my PhD thesis, computing equivariant homotopy with a splitting method. First, I want to introduce the background of my research. Equivariant homotopy theory studies spaces and spectra which admit actions of a fixed group. It was motivated from and applied in geometry, algebra, and other branches of topology. One of the most important applications was given by Davinus and Hopkins in chromatic homotopy theory. It shows that the localization of the sphere spectrum with respect to the Moldova K theory is equivalent to the homotopy fixed point spectrum of the Moldova E theory, which is acted on by the Moldova stabilizer group. In other words, the non-equivariant information on the sphere spectrum can be obtained by some equivariant computations on spectra acted on by Gn. In general, however, the computations in the equivariant world are quite hard, since the additional group action brings extra complexity. There are lots of computations done when the acting group is cyclic with order p, while some of them can be extended to the case of Cp². For larger groups, there are some computations on the Eilenberg-Maclane spectra and complex cobordism, but in general, we know very little about how to compute equivariant homotopy when the group becomes larger, especially when the group is non-abelian. My thesis provides a new method in such computations, which we call the splitting method. The main idea is we can make spatial splittings on the homotopy of G-spectra, and most of the split pieces can be decomposed into homotopy of spectra acted on by P subgroups of G. In other words, if G itself is not a P group, we can always compute the homotopy of G-spectra in an inductive way. The motivation of my research traces back to the study of rational equivariant spectra by Greenleaf and May. In the rational world, the category of G-spectra is split into small pieces. The homotopy of each of these pieces is not hard to compute. However, we also lose the torsion part in such splitting, so we need to make some refinements. The idea is, if we invert some but not all primes, there will be a weaker splitting, but the split pieces may still remain computable. We can apply this idea multiple times with inverting different collections of primes, so we can obtain different torsion parts of the homotopy and finally glue them together. As an example, assume that we are computing the homotopy of some spectrum X acted on by the dihedral group with order 6. We can invert 2 and 3 separately to obtain weaker splittings, which enable us to compute this localized homotopy of X. Then we can use the localized homotopy to recover the integral homotopy. The key element in our splitting method is the special class of G spaces EF. It is characterized by its fixed point subspaces, which are either contractible or empty. We constant the natural map from EF plus to S0 and write its cofiber as tilde EF. Then, after inverting certain prime factors of the order of G, we can split the category of G spectra into two pieces by multiplying with either EF plus or tilde EF. In our splitting method, we will consider the following special class of families. We consider the family of all subgroups whose orders only contain certain primes. The splitting happens if we invert all other prime factors of the order of G. Now we can explain the main procedure of our splitting method. First, we fix one prime factor P and invert the others. Then we consider all families such that the splitting happens and split the category of G spectra as much as possible. If we can compute the homotopy of all these pieces, then we get the localized homotopy of X when all prime factors other than P are inverted. We can choose different P to compute different localizations of the homotopy, and then recover the unlocalized homotopy from them. The hardest part of this procedure is the computation of the split pieces, for which we divide into two cases. We will have either lambda sends some I to EFI plus, or lambda sends all I to tilde EFI. Case 1 contains all pieces with exactly one exception in case 2. For case 1, we can rewrite the summand as the product between EFI plus with some G spectrum Y. Then we can apply the following theorem. The rough idea is the homotopy of EF plus smashed with Y can be decomposed into homotopy of Y with smaller acting groups. Since G itself is not inside the family Fi, this theorem enables us to finish the computation inductively. For case 2, we can express E lambda as tilde EF for some special family F. So we can use the properties of its fixed point subspaces to greatly reduce the types of G cells. To be precise, all G cells with isotropy groups inside FP will be eliminated. There are two ways to apply this theorem. First, we can reduce the number of irreducible representations, since some of the representation spheres will be equivalent to S0 after smashing with E lambda. Second, we can simplify the spectrum X if it comes from some cell complex, or more generally, if it is constructed from some pre-spectrum. The method we use for case 2 is less general compared to case 1, but it still works for special choices of X. As an example, we will use our splitting method to compute the homotopy of the Eilenberg-Maclane spectrum Hz, when G is the dihedral group D2P. We invert 2 first. Hz will be split into 2 pieces, while the homotopy of the first piece can be decomposed into the data about CP spectrum, and the second piece turns out to be trivial according to some homological arguments. The same thing also happens when P is inverted. We have one piece decomposed and the other piece being trivial. Since the C2 and CP homotopy of Hz is already known, we can use all information in this page to obtain the localized D2P homotopy of Hz with either 2 or P inverted, as listed here. Finally, we just need to trace the generators in these two equations and glue them up to get our final answer, the unlocalized homotopy of Hz. If we focus on the Eilenberg-Maclane spectra, the existed computations, when the acting group is some special P group, become the building blocks. We have the following list of equivariant Eilenberg-Maclane spectrum, whose homotopy becomes computable after applying our splitting method. This list could be longer in the future after we know more information for P groups and obtain more building blocks. Finally, I want to talk about some current and future directions of my research. I have done computations only on Eilenberg-Maclane spectra, but the splitting method itself is quite general, so I want to apply it in the computation of other equivariant spectra. I have special interest in the equivariant complex cobordism spectrum, MUG. In some sense, MUG is even more computable than the Eilenberg-Maclane spectrum because of its structure as a Thom spectrum and a special evenness condition on its homotopy groups. Some computations are already done by Chris and his colleagues when G is abelian and when G is D6. There are other studies on the geometric fixed point spectrum of MUG, which traces back to Tom Dick. I would like to see how those computations can be generalized and interacted with my splitting method. The equivariant complex K-theory is another option. Although KUG itself is somehow less computable than MUG, it might be possible to obtain more information from the deep relation between KUG and MUG. Another direction I'm interested in is the computation when G is a P group. This is the case where our splitting method cannot be applied. I'm interested in the application of the generalized Tate diagram. The cofiber sequence we are using in the splitting method is in fact the first line of the Tate diagram. When G is a P group and no splitting happens, we have to take the second line into consideration in order to solve the extension problem. It is applied in many different equivariant computations, including the computation of MUG above when G is abelian. Another idea of my interest is the interaction between the splitting method and some special spectral sequences. There are two examples I have in mind. The decomposition theorem in our splitting method works well for the sliced cells and in the construction of homotopy fixed point spectra. So I would like to see if there are any possible applications in these two spectral sequences. So this is the end of my talk. Thank you for watching. I will be in the first session from 12 to 12:30 in the Employment Network program. If you're interested in my research, please come by and have a talk.